U-substitution is a very helpful type of integration technique and is commonly thought of as the reverse chain rule. However, if we think about it in a different way, we can better understand different parts of calculus like the Jacobian the or trig subs. We can use U-substitution when we have a function f of g of x times g prime of x dx. And we just replace g of x with the variable u, which makes the integral easier to solve. However, since we're changing the variable, the differential is also going to change. So we want to write the integral just in terms of u and not in terms of x. We see here that du is equal to g prime of x dx. And we can rearrange this and find that du dx is equal to g prime of x. And then as we see here, basically what we're doing is we're writing the same integral and replacing g of x with u, but also dividing by u prime, or the derivative of u with respect to x. And then we end up with the integral of f of u du, which can be a much easier integral to solve. The big question is, why are we dividing? Why are we not just replacing g of x with u? Why do we also have to divide by u prime, or the derivative of u with respect to x? To better understand this, we need to take a look at what happens when we change the input to the function g of x with u. Let's say this is a graph of the function f of g of x, and then we have x on this axis. To understand transformations, we should look at a certain part of the function. These two values a and b represent the bounds for the function. Now when we change the input to u, we get a similar graph. We can see that the output at the bounds are the same because u equals g of x. Therefore, the function f will output the same thing for the inputs g of a and c because g of a equals c. Notice that all of the values of the function f in this graph are also encompassed in this graph. They are not all at the same spot, but they are all there because the inputs to the function f on this graph have to correspond to an input to the function f on this graph. Now we can see why we can't just integrate this function with respect to x and this function with respect to u and expect to have the same result. Because both of these graphs have the same heights, however they have different widths. Therefore, the area of this region has to be different than the area of this region. So now, when we want to integrate this function, we just need to fix the widths because the heights are already the same. As it is often in calculus, it can be helpful to think about this with extremely thin rectangles. Now what we need to answer is how much wider this rectangle is than this rectangle. Notice that on this graph, x determines the width of the rectangle, and u determines the width of the rectangle on this. We know that du dx is the rate at which u increases with respect to x. Therefore, the instantaneous change in u is du dx times as big as the instantaneous change in x. So this rectangle is going to be du dx times as big as this rectangle. Therefore, if we want to resize this rectangle so it has the same area as this rectangle, we can just divide its width or height, whichever way you want to think about it, by du dx. Now when we take a look at our original definition of U-substitution, we see that we are changing the function to be in terms of u, then dividing by g prime of x or du dx, which is really just scaling the width of the function in terms of u to match the width of the function in terms of x. So the main takeaway is that this part changes the variable to make the integral easier to solve, and this part accounts for the change in width that occurs when the variable is changed.